BSides DC would like to thank all of our sponsors, and a special thank you to all of our speakers, volunteers, and organizers for making 2018 a success.
Good afternoon, everybody. I am Daniel Orlando, and this is
Advait Nagarkar.
And we're presenting a talk on encrypted network traffic and detecting malicious activity in encrypted network traffic. So we are from Fidelis Cybersecurity. So first of all, network traffic is sequential. It's a sequence of sessions, one after the other. Some of these sessions may be encrypted. And so for example, first you may be, as an example of malicious activity, first you may be referred by a hidden iframe. You may visit a landing page. Malware may be downloaded over TLS, ping for connectivity, and then steal data over TLS. So notice that a lot of these sessions are encrypted, and in fact, a lot of the critical sessions where important malicious stuff is happening is encrypted in this example. So, but also there are some of these things that are in the clear. So when it pings for connectivity, that's in the clear. The hidden iframe may be an HTTP page. And the idea is to use the structure of how the sessions flow to understand whether this is actually malicious traffic or not. So first we're going to talk about some of the data we use to train this model, some of the features we extracted, which features are a numeric way of describing data that the algorithm uses. And then some models. So once we actually have these features, how can we use these features to train the models? And then we're going to look at some results. We're actually going to peer inside from feature extraction all the way to inference, model inference, exactly what is going on at each step of the process. And then finally, we'll give an illustrative example for how this is working. So first, the data. The malicious data we have are suspicious files that are submitted to the Fidelis Sandbox appliance. And these files are run through a sensor and generate PCAPs. And our in-house threat researchers also find files and submit them as well. They have feeds that they can see latest files and submit them to the sandbox. So we have PCAPs from customer submission and threat. And another issue is labels. So with supervised learning, there's a fundamental question, which is, what are the labels? Is this data an example of a cat or a dog or a horse, for example? So we need to know which these samples are. Are these malicious? Are these benign?
Right, because we're taking submissions and going through, well, in addition to the feeds where everything's obviously labeled as malicious, we take submissions, so we have to label them first, and then we can use them for our algorithmic training.
Yes, so this is primarily from AV and our own rules developed by the threat researchers, and we use samples which are highly confident that these are indeed malware. So for example, on something like VT, there are a lot of different high scores from the vendors to confirm that they are indeed malware. And that comes to around 36,000 samples.
That we used in the training for this particular exercise here.
Yes. And as for the benign data, we could use submissions labeled as benign, but the issue is that these submissions to the sandbox are not in general representative of general network traffic. So what does this mean? If you are a user who is using a computer, browsing some stuff on the web, that may look different than the network activity of, say, a Word document or an executable that is being submitted to this, even if the executable is indeed benign. So the idea is, if we want to use this in production with live traffic, then the benign data actually has to look like live traffic. So what we do is we supplement the benign samples in Sandbox with DMZ network traffic. And that comes to about 51,000 samples from benign submissions and another 270,000 samples from this general traffic. So, adding it up, it comes to about 320,000 benign samples. Another question is, if you look at the samples that we had for the malicious, so the malicious data, what we had is a sample being submitted, and then all the sessions that came from that sample detonating in a sandbox. So how does this correspond to live traffic then? The idea is to put a hard limit on a 2-minute continuous sequence of sessions. So there's a certain threshold, one session after another, and a requirement that's within a 2-minute window, because the whole idea of machine learning is you have to have, if you're doing a classification problem, you have to have an apples to apples comparison. So for example, if you were trying to classify between a picture of a cat and a picture of a dog, it would be problematic if on one hand you had photographs of cats and on the other hand you had drawings of dogs, for example. So the idea is you want both of the classes to be similar. And finally, we're going to talk about the features. So again, as I was saying, you have the raw data, which are the proxy logs, and we want to extract features. We want to come to vectors which describe the data. So this is a really large problem in any space. Image recognition, there are many ways to get vectors from images. Text, there are many ways to get vectors from text. And in this case, we actually want to use one of these ways to get vectors from text. So we're going to use some natural language processing techniques and talk a little bit about what that means in this context.
But also, in cases of encrypted traffic, obviously you can't see the text, so you can't do your standard text analysis. So there we use the certificate classifier that we presented at last year's BSides as a supplement for the cases where we don't have direct natural language processing type features.
Precisely. And so the idea is what we can see, what we do have detailed visibility into, we will use, and then what's a little bit more opaque, we'll supplement with the certificate classifier. And we're going to talk about, this is text, how are we going to use NLP to understand this and convert this to vectors? So a simple way is to use some technique called bag of words and one-hot encoding. So for example, here, this is a document. It's a very short document, just one sentence. The tuxedo cat, it's a phrase, not really a sentence. And the document has a very small vocabulary. It only has 3 unique words in it. The, tuxedo, and cat. So the vectors that we're going to use to represent the words in the document are going to be the size of the vocabulary. And each word is going to be represented by a one-hot encoded vector in this space, which means it's 1 in one place and 0s in all the others. So the, we could arbitrarily represent with this vector here, 1, 0, 0, tuxedo, 0, 1, 0, and cat, 0, 0, 1. And now that we have this phrase, we want to represent this document as a vector. So each of these words has a vector associated with it, each of the words in the vocabulary. So we can aggregate them together simply by taking the sum and get what's called a document vector. So this is a document vector representing this document, the tuxedo cat. And the idea of using this in the context of sessions is that if each session we can represent by a vector, using a technique like this, there are many tokens in a session, so we can aggregate them to get a session document vector. But we actually want to talk about sequence of sessions, not just one session. So the idea is our input data would be a sequence of document vectors. That's great. And in fact, that's the setup we're going to use. But the problem is there's too many dimensions. So we can't use this bag of words approach where the dimensionality of the vectors is the size of the vocabulary, because the vocabulary is huge. The English language already has huge vocabulary. French, Spanish, huge vocabulary. But if you take something like cybersecurity, there's just a whole world out there and a very large vocabulary. So a solution is word2vec. And word2vec is a very popular approach these days for doing representation of text. So for example, even something like Google Translate uses a sequence-to-sequence neural network with word embeddings, so with word2vec or possibly some other kind of embedding.
Well, they invented word2vec for Google Translate.
Yes.
So yeah.
For Google Translate?
Yeah, I'm pretty sure.
Oh, well, but yes, they did invent word2vec. And the idea is, if we go back here, notice that the vectors in this space are very sparse. It's a high dimensional but sparse space. And by sparse, I mean it has very few values that it can take in this space. So, there are very few vectors in this space. They only have the values in the components 0 and 1. And actually, why not have a lower dimensional space where the vectors are more dense in this space, which is to say that the components of the vectors can take all real values. So instead of going 0 to 1, integers between 0 and 1 inclusive, those are only 2 integers, you could have the uncountable set of all real numbers in each of the components.
Which allows a massive dimensionality reduction.
Exactly. And more capability of expressing all these different words in this lower dimension. So the idea of word2vec is you train it on a corpus of data, and it's trained to recognize possible context from a word. And it actually uses a shallow neural network to do this. But the interesting thing is, once you do this, it recovers some very interesting semantic information. So
the dimensions in basically you're using the word2vec model to transform your very sparse representation into a dense representation, and the dimensions in your dense representation are these semantically meaningful dimensions.
Yes.
It turns out to be the case.
Yes.
And so, like, as we see in these examples, the dimension that in the dimension of, like, grammatical gender, for example, the word king is in one place and the word queen is in another, the word man is in one place, the word woman is another, or in the semantic dimension of present tense to past tense, the present tense are all on this side, the past tense are all on that side. And so you end up with, the model the neural network in the word2vec model actually learns the semantic, infers the semantic variation within your training set.
So back to the title of the presentation, actually, this is a good point to mention it. That's the whole idea of network traffic as an open book, because we are using natural language processing techniques. So the idea is visibility into encrypted traffic, but also using these natural language processing technologies. So now that we've talked about the features, we can talk about building models using these features. So one possibility is random forest. This is a very popular algorithm to use. But a limitation of random forest is, as we talked about, we have each sample. One way to aggregate these vectors together in order to feed it to random forest is to just take the mean. And so yes, so now we can use random forest. But for those of you who don't know what random forest is, I have a small example here. A random forest is it's what's called an ensemble classifier of decision trees. And a decision tree is this flow, it's sort of like this flow chart over here with this root. So it's a flow chart with a root, and as it branches off, it makes different decisions. So this flow chart over here is representing if somebody died in the Titanic or not.
This is the canonical textbook example of a decision tree.
Yes, slightly morbid. But yeah. So, one of the first questions you might ask is, are they male or not? And right off the bat, if they're not male, there's a high probability that they survived.
Women and children first onto the left.
Exactly. So that's what this whole thing is representing, actually. Women and children first, and a decision tree.
You go by sex is the way a decision tree gets trained is it looks through all the features you have, and it figures out which one has the most predictive validity for the set of data that still exists at this stage of the flowchart. And so you start off, you have everything, at which point the women mostly survived is a pretty easy prediction to make, but then within the men, you have to look, I mean, the old ones mostly died, and then the children, it actually turns out, interestingly, to be depending on how many adults were accompanying the children, whether they survived.
So, and this actually is a great decision tree, but if we have on the order of several hundred features, which is what we're looking at if we have 100-dimensional vectors, then what happens is if you train a decision tree on these features, it has a tendency to overfit, which means that it'll have difficulty generalizing to new data. So one way to offset that overfitting is to use this ensemble classifier random forest. So it's like having multiple experts in a room, and they each have a random subset of the features. They each have different strengths, but together they can come to a very well-informed decision.
So the wisdom of crowds as applied to these machine learning algorithms.
Yes, and so that actually did pretty well, very well. 98.9% accuracy with a high AUC of 0.9976. But we can actually do better than this. So the next step is to use a recurrent neural network, which takes into account this information of this sequence of vectors. So it uses the information about ordering of the sessions, and the idea of how recurrent neural networks is, for each example, you have multiple vectors, and you keep feeding in vector after vector, and these horizontal lines are the weights that keep getting updated as you feed in each next vector. So it turns out that the most important feature when we use a recurrent neural network ends up being the certificate classifier score. When we train the random forest, we use the certificate classifier score, and it had an AUC of 0.9976. And then when we train the recurrent neural network without the cert classifier score, the accuracy went up, but the AUC went down. And the AUC is the measure of general quality of the model as you vary the predictive threshold. So maybe you decide you really want to make your false positives low, meaning that you only predict a positive if you have a higher threshold. So AUC is a way of measuring, aside from the standard cutoff of 0.5, how it does over many different thresholds.
It refers to the ROC curve, which
area under curve.
Yeah, and so the curve itself is it's a characterization of a model, and it's a standard signal processing metric that we use. But at any rate, I think the main point is, so using the better model drives up the accuracy quite a bit, well, or rather cuts down the inaccuracy quite a bit. I mean, once you're approaching the plateau, it's a little incremental, you get diminishing returns, but as far as it goes, you can see that actually the cert score makes a difference, but at any rate, it's really the switching from basic sequenceless traffic to, or characterization to the sequence-aware characterization of the features that really gives you the oomph in actually classifying traffic.
So now that we've talked about the data, the features, the modeling, we want to show some concrete results of actually what this looks like from beginning to start and actually peer inside the model. So first off, what you're going to see are several 2D visualizations, but keep in mind that we're actually visualizing 150 dimensional data and more. So what we're going to be using to reduce the dimensions to show you, because at least I can't view 150 dimensional spaces, but is t-SNE. So t-SNE is an award-winning dimensionality reduction technique that essentially builds a probability distribution between the similarity of every 2 points in this high dimensional space, and has it projects down to 2 dimensions or 3 dimensions or whatever dimension you choose to reduce to, and make sure that probability distribution is preserved. So here are the 5 stages that we're going to visualize this on. One stage is the transaction level word embeddings, because within each session are the transactions.
So these are the various network operations that the HTTP operations, for example, in an HTTP session.
Yes, and then you assemble these transactions, and you get sessions. And there are certain things that are constant now across sessions, but are not constant across transactions. So these are the tokens that are at the session level. So we have 2 word embeddings going on, and we assemble them together to get the document vector, which represents the session as a whole. So remember that each sample is actually a sequence of sessions. So once you have a sequence of these document vectors, then you actually hand it off to the RNN. So the RNN is seeing the recurrent neural net. So the RNN is seeing a sequence of vectors, and we're going to look at the activations in the first layer, and then we're going to look at the activations in the second layer. And okay, so these are the transaction level token embeddings, and this is the same plot. If you look at the shapes, it's really the same plot, but we're actually looking at it across these 2 different dimensions of malicious and benign. So malicious is red, benign is blue on the left chart there. And on the right, we are actually looking at these different kinds of tokens. So there's a high frequency of tokens from URLs, tokens from hosts, different things.
Right. These are the different fields in the proxy log that give us token quantity in the different so each of these points is a session, and the color corresponds to what sorts of tokens.
So what's interesting here is not so much the picture on the left, because since we're at a very low level, we're not seeing a lot of separation between malicious and benign samples. They sort of have similar tokens. There are clusters of blue tokens. There are little pieces that are predominantly red, but overall it's really muddled. What is interesting, though, is that the word embedding does learn very distinct things about types of tokens on its own. So keep in mind that I'm not telling it some additional information about what kinds of tokens these are. Just like if I was training a word embedding, I wouldn't be telling it that this is a verb, that this is a noun. It just automatically figures that out on its own from context.
Right, so basically the different colorations of these different regions correspond to the word embedding having learned different semantic properties of the different classes of tokens in the proxy logs.
So a word on the axis, if you're confused about pi1 and pi2, recall that we are visualizing a 2-dimensional projection. So pi is just a mathematical, lowercase pi is just mathematical notation for the first projection and the second projection. Remember that this is actually...
These are sort of contrived dimensions here for the visualization purposes.
And then it actually gets a lot more interesting with tsni, with session level tokens. So here again we have predominantly a component with predominantly D port on the right, and other stuff on the left, which of these other things, it's primarily S and I actually, and there's a lot more variety on the tail of that over there. But if we look at the figure on the left, again, the D ports are very muddled. There's some benign, some malicious. It looks like.
Yeah, the main point here is that by the second, in the session level tokens, you can see we got quite a bit more structure in terms of the semantic. Whatever. Between the semantic, it was perched on the edge of the table. Whatever. Anyway, so basically, you can see that we got substantially more clean structural understanding of the semantic meaning of different types of tokens at the session level.
Because it is higher level than transactions.
Right. But again, so these semantic tokens don't really, the presence or absence of these tokens doesn't really correspond to a label, because, I mean, you're going to have destination ports in malicious traffic and benign traffic, right? So, yeah, so moving on to now we're actually...
Yes. So this is by the time you aggregate all the vectors, all the word vectors from the session tokens, all the word vectors in the transaction level tokens, and you assemble them into the document vector 1 for each session. And this was very exciting when I first saw it, because it goes along with your intuition that some sessions will definitely be malicious, and you will only see malicious traffic. Some sessions are benign, and you probably only see benign traffic. But there's a lot where you see it's mixed. So I don't know if it's very clear.
You have this muddle here, you have a bit of a muddle here, you have a bit of a muddle here. Even in places where it's relatively clean, it's still a little bit muddled.
Yes.
But there are some regions where it's relatively clear, and some regions where it's sort of isolated. So.
But the idea is that since we've gone up a level, we've gone up from transactions to sessions, and now our session tokens, to now a whole representation, an aggregated representation of that whole session. We really start to see some significant separating out between what really looks like malicious and what really looks like benign.
All right, and so this is now, we can look into the sort of knowing on the left what the labels are for the different regions of this contrived projection space. We can look and see what are some different features that correspond to different locations in that space.
Yes, so that orange down there, for example, that's from the UK.
Yeah.
That green up there is from Russia. China is down there.
Well, there's some traffic that goes to China from here. There's some traffic that goes to China over here. But in general, you can see that actually the traffic going to different countries is relatively, I mean, there's some muddle in the middle, but there are some regions where it's quite clearly defined that the traffic in this area is bound for one destination country versus another destination country.
Yes, and then the grayed out blobs there, which, as you see, it's not really in the color coding, are unknown countries, so that's like DNS requests that we may not know.
Well, not just mostly unknown, but also, I mean, we're only coloring 5 of the countries.
Yes.
But I mean, there are other countries in the world, obviously, and so, but yeah. So moving on, this is a different coloration of the
so as you see, there's a lot of DNS requests in the data. This piece over here are DNS requests that we're only seeing in malicious data. Mainly, there's a little bit of blue specks in there,
right.
but a lot of that is malicious DNS requests. And these ovals on the outside are, some mixed, some benign DNS, and for our purposes, the most interesting piece over here is this right hemisphere.
Yeah, this big malicious blob in here, which corresponds to this, which is, I mean, there's DNS, but then this is where you see HTTP and TLS traffic.
Yes, so TLS, and focus on that. Remember that TLS is on this right here.
So you have this center blob. The bottom is not so interesting, but the top, you have the right side, that's the TLS. So watch that.
So now that we get to file type, we actually see that a lot of the file types in that TLS section are actually certificates, and the
rest is text, because I mean, once it's encrypted, it just looks like binary ASCII text.
Yes, and then as for HTTP, there's really a lot of JavaScript, binaries, JPEGs, things like this, which is exactly what we'd expect. And then how much? So what's the session size? And we see, this is kind of interesting. On the outside, remember, there was a lot of DNS, and we see that variety of DNS sizes in the malicious But the interesting thing is that green appears to be more prevalent, so there seems to be mid to high in DNS. And then HTTP and
these are all mostly 0 because the size didn't get, it's not a well-defined property in those sorts of cases based on the definition of the feature we're using here.
If you remember what all I was going to show you, there was the the transaction level word embeddings, the session level word embeddings, the document vector level aggregation, and now we're actually going to start to look inside the model. So before we actually go into the model, I want to talk a little bit about machine learning theory so you understand these visualizations. First, there's this concept of a decision boundary. If you have two sets of points, for simplicity, that you're trying to differentiate between, and you have a feature space, so two or more numerical ways of measuring the differences between that space, then what a machine learning algorithm is actually doing is it's doing some kind of regression problem. So it's learning this boundary between these two classes, these salmon and sea bass, along these two different dimensions, width and lightness. So for example, right off the bat, you see that lighter fishes tend to be the sea bass. And the idea is that when you have really good features, the decision boundary is going to be more clear. And another thing is that why is there so much hype about neural networks? So the hype about neural networks is actually that neural networks generate their own features in the sense that the layer before the last layer is creating features for the layer after it.
Right, so the input to each layer is the features that that layer is using, and then the output becomes the input to the next layer, and so it's the features that the next layer is using, and then the output of that layer becomes the input to the next layer, which are essentially the features that it's using. So after each layer, you're transforming your feature space, which gives you new features that are hopefully more clear, or that hopefully provide a more clear illustration and separation of the different classes.
Yes, so this is what the first layer looks like. And then by the second layer, we see that it's very well separated out.
Yeah.
And
so this is the process, right? So you go from here to here. This is the transformation from one layer to the next.
Yes, and just to illustrate how useful the search score was in this is the same recurrent neural network trained without the search score. So you see that by the time you get to the second layer, there still is quite a bit of separation.
But it's not the same type of improvement. Like, and this is, you could by hand just write out the function that goes here as like a piecewise linear function, and then just by looking at this, you could get almost great results.
Yes. So great. Now that we've looked inside the neural network, understand how all the features work, what is a concrete example of how this classifier is actually run with an actual piece of data? So I went into some of the data that I was using and picked out one example here. So here's an example where the probability coming from the classifier was that it was malicious is very high, and this is actually a known malicious sample, so it's fitting that it has a very high probability of malicious because it is in fact malicious. And the search score is also on the high side for one of these sessions. For a couple of them looks like.
So here, for the sequence, we're taking the highest score for the certificates, for all the different certificates that comprise the session. And so here you can see this is the sequence of sessions. It starts off, if you want to walk through it.
It starts off with a couple HTTP web pages, one with Google APIs. Then it goes to vid7.com. And it does a lot of stuff in the US, but it has one session, HTTP, with Russia, fastpick.ru. And there were some pornographic web pages in this data. It's sketchy stuff.
Yeah, but at any rate, once it redirects to this exoclick site, you end up with a very suspicious certificate.
Yes. Oh, and actually, I looked up easylist.club, and don't go to that website. It's it's definitely bad. I did not click it, but Google search easylist.club, and the first result was how do I get rid of easylist.club virus on my PC or something like this. So
yeah.
And so each of these sessions gets represented by a document vector, and these are actually where those document vectors landed. So you see there's one that's smack dab in the middle of that red zone right there. Some on the periphery, these I guess are DNS requests. And so here's where it landed in the recurrent neural net. In the first layer, it was in this red piece over here, and by the time it got to the second layer,
it's well towards it's
yes.
deep into the malicious territory, right?
Hence the high probability.
This is a clear example of malicious traffic, so it's fitting that it ends up very, very far from our sort of visual
decision boundary,
rule of thumb decision boundary here.
Yes. So let's to sum up. We've analyzed sequences of network traffic and used word embeddings to extract our features, so to turn the raw proxy logs into numeric quantities. Then we've trained an ML model to identify these malicious sequences of sessions, and we've leveraged the cert classifier, the certificate classifier, this knowledge of this may be a suspicious cert or not. And finally, the results are very encouraging. So some next steps would be to investigate possibly mislabeled training data.
So if you look back here, you can see that we have some of these labeled benign samples that are sometimes very far into the malicious territory. And so we've started investigating them. Some of them look a little suspicious, but we haven't concluded that investigation yet. But certainly there are some suggestive results there that maybe our labels are
right
not
off
the
the
best.
bat is that, I don't know if you guys can see, but there's a little blue dot next to my star over here. So there's actually one sample that I can start by investigating that should actually be very structurally similar to this malicious sample that I just showed you guys. So that would be very interesting to look at.
And yeah, so this is all with, I mean, we got a small-ish training data with only a few 100,000 examples, so we'd like to, going forward, maybe redo this exercise with about 10 times or 20 times, 50 times, 100 times as much data, see how that affects the results. I mean, already with the hundreds of thousands, you're probably in your statistical limit there, but it's good to check. And then, once we've done all that, then we want to put this in our product. So, productionalization, so testing, validation, integration with the production code base, et cetera, all the regular stuff. And
but an important thing here is to monitor performance, set up infrastructure for automatically monitoring this classifier and doing periodic training if need be.
Right, because, I mean, this is all based on the thing to know about these. If you're using machine learning and you have a model, that model is trained based on, that model is making inferences based on the training data it had. And so, as threats change, as there are new types of malicious behavior, new patterns of malicious behavior that are invented, the training set we use is going to grow increasingly obsolete over time. And so the goal is to eventually be in a place where automatically every month or week or several months or however long it turns out to make sense to do.
Part of the performance monitoring.
Right, based on our performance monitoring, we would then want to just have it automatically retraining or building a new model based on that newer example data.
Great. Questions?
Sure.
Yes.
Performance monitoring in this context, it sounds like it equates to sort of a sanity check.
Well, I mean, a sanity check is one thing, but here we're talking more in terms of just in general looking at, so this would be in the context of, classifying malicious traffic. So, periodic, looking at a sample of the predictions it's making and checking to see what fraction of them are correct based on other sources of labeling, and comparing the results of our model to other sources of identification of malicious traffic, and doing that in an automated way. So we automatically run all this traffic through various antivirus engines and our threat rules, and we have lots of other ways of figuring out what's malicious. And so comparing the results of this to that over time to make sure that as we are sort of updating all these things in tandem, that they're sort of continue to agree with each other going forward.
Great, thanks. And so, do you foresee though a time when your classification, this model, might fail that check in the sense that it has unearthed something that none of those other methods is actually, so...
Sure. Yeah, I mean, right, yeah. Right, yeah, and definitely that's one of those things, like even as we were saying, even in our smallish, well, relatively small training set, we found some things that look like they're suggestive of mislabeling. And so definitely whatever infrastructure we end up building out to do that investigation more thoroughly is certainly worth applying to just these monitoring activities going forward, yeah. Yeah, because I mean, definitely the goal is that you have multiple different sources of knowledge and you're enriching each based on the other, and you're bootstrapping your way up to a better understanding. Yeah. Any other?
Yes, sir.
Any approaches that have emerged since you started this work that you'd like to explore, or areas that you didn't explore in this work that you prefer?
Yes. So potentially explore different, more nuanced way of extracting features. So one thing, for example, that's been done before is weighting using TF-IDF, the different vectors. So what this would do is this would emphasize more rare-ish, more significant kind of tokens. And the weighted sum, it would be a weighted sum instead of an average to get these document vectors, and you would be emphasizing
the more unique.
Yes.
Yeah. Yeah.
Thank you. Any other questions? Yes, Mr. Kreitz.
You showed an example where you compared the results of the model to be able to classify something without the certificate score.
Yes.
And then with the certificate score, it's a little bit better.
Right.
With the extra score.
Yes.
And the certificate score is the subject of another talk that
Right.
Last year.
Last year.
So you guys are what does it look like if, so we saw without the certificate score with, versus, so everything with except the certificate score, and then everything plus the certificate score. What is, how accurate is the model if you forget everything but the certificate score? In other words, how good is it if I just say, well, this certificate score is actually really the predominant solution?
Yeah, so
I don't know that we have those numbers.
no. I don't have those numbers off the top of my head, but I definitely did look at directly how the certificate score correlated with malicious sessions. And I think the issue with that is that sometimes not the critical stuff wasn't happening in the encrypted sessions. The payload could have been delivered in the clear and just have gone to some refer page over TLS. So there could be many instances where the certificate score wouldn't come in handy, but it definitely is useful in the case that there is actually critical stuff that is happening in TLS.
Yeah.
So like I said, I don't remember off the top of my head, but my recollection is that it wasn't enough to be convincing on its own.
Yeah, and especially if you look at our example here, you see that some of these, like this EasyList.club, which is, I mean, that is itself is like that he Googled and don't go there, the score is much lower than this add certificate. And this, these exoclick certificates are much more suspicious than the easylist.club certificate even. And so, it's a great feature to have, but it's not, we still gain a lot from knowing that you had like a sequence of different different events.
Yeah, there are several tokens or whatever you would call them within this session
Right.
that don't have a high search score.
Right, yeah. Yeah.
It's the sum.
Right, exactly. It's the context. When you have everything in context, you can see that together it's very suggestive in a way that by itself it might not be.
Any other questions? Yes, sir.
This relates to the features that you guys are looking at. Have you guys looked at using flow-based statistics, or is that not possible with your data set?
It would absolutely be possible. So that's actually an important note that I want to. Are you familiar with recurrent neural nets?
Somewhat, yeah.
So the idea is you have each. A recurrent neural net is, like I was saying, it's a sequence of feature vectors. So one option is to put the cert score in each of these feature vectors as an additional component. But what I've decided to do instead is have, at the last layer of the neural network, a linear combination of the max cert score and whatever the vector coming out of the RNN is. And so then there becomes a weighting between the maximum cert score and whatever's coming.
Essentially, we have a staggered input layer.
Yes. So basically, if there's any other features that we want to tack on, like these flow-based statistics, we could absolutely do that easily, and that would be an interesting thing to investigate.
Definitely. Having the architecture as it is, I mean, the recurrent piece picks up. We have a couple of recurrent layers, but that's not the only input. So certainly we could add other things.
Okay. Any other questions? Okay. Well, thank you very much.